Good morning, everybody. Today is December 2nd, and we are beginning our last section of Mechanics of Materials, and the title of this section is Combined Loads. So as we take a look at our Moodle page, the material that we're going to be covering on combined loads is not available in your textbook. It is there, but it's in a less usable form. So on Moodle, I would like you to go down here in the week of November 28th through December 4th. You'll see that there is a file entitled Notes for Combined Loads / Moore's Circle, and that's the material that we're going to be using for this particular section. And this will be the last section that we'll be talking about in the textbook. So you are going to not have to open your book again unless you need it as a reference. So what are combined loads? Well, basically, I'm going to go over here to the document cam, and we'll switch back and forth between these two for the lecture today. What we'll see with combined loads is, so far, we have broken everything that we load a beam into axial loads, transverse loads, and bending moments. And we really haven't even developed a really good sign convention. So I'm going to draw you this little picture like this. And this is the positive sign convention for each of our three types of loads. In other words, pulling, tension, positive bending moment, and if we cut on the right, a shearing load that goes downward. Okay? So those are our three positive sign conventions. Now, if we were to cut the other way, once again, we would have a pull, we'd have a positive bending moment, and our shear load would look like this. So those are the two positive sign conventions. But when we talk about combined loads, what we're really talking about is sigma and tau often occur together. In other words, we may have more than one load that we apply to a structural member, and due to that, we're going to have both sigma and tau, and we can have sigma from a couple of different sources, as you can see here, and it's split between two different pages, so it might be easier if we, well, I'll just talk about it this way. We have sigma, or normal stress, from a P over A, or an axial load. We have tau, shearing stress, from a torsion in the amount of TC over J. And then we also have sigma from a moment, which is in the amount of MC over I, and that tau from a shearing load, VQ over IT. So what that means is that we have four possibilities, two for sigma and two for tau, and they may occur together in the same loading situation. So here's the deal. In order to analyze structures that exist in combination with each other, we use what is called the idea of superposition, which means all of the sigmas will add together at a particular point, and all of the taus will add together at a particular point. And so this equation, sigma total equals sigma axial plus sigma bending, and tau total equals tau bending plus tau torsional, means that if you can analyze how they work independently, which we've already done in each of these cases, then you can add them together as long as you keep your sign convention correct. And when I say add, I mean vectorially add. The direction is taken care of because sigma is always perpendicular and tau is always parallel to a surface. But if you add them, if you understand that they may either, the absolute value may increase or decrease depending on whether it's, whether they have the same direction or not. I'm just talking about the same direction as equal or opposite because we've already resolved our directions. Then you can use these equations in order to compute the total normal stress and the total shearing stress at a point. So this part of your notes gives you the steps. Draw the free body diagram, which is always necessary. Do your statics, solve for the external reactions. Redraw the free body diagram with the external loads applied. So in other words, you substitute R sub A or a support. You substitute the magnitude of that load and the direction. You do the cutaways. You cut the body at a point of interest and draw a free body diagram for that cut. Then you identify and solve for unknown torques, moments, shears, and axial loads. So we've done steps 1 through 4 so far. 5 is just a little bit more involved, but we've done it for these individual things before. And then we calculate the normal and shearing stress for each load type. And then we add them together using the principle of superposition. All right, so here's an example. We want to find the state of stress. State of stress just means sigma total and tau total. And we have a body in figure 16.1, which we'll talk about. We have assumptions. The given FAS stands for figure as shown. And we have some assumptions, and then we go ahead and work our problem. So one of the things I want to show you here at the top of page 289, this is the way that Dr. Bailey draws a structural member. The support at D, the triangular support, represents a fixed support, and the circular support at E, the circle, is a rolling support. So the reaction at E could only bear a force in the y direction. In the x direction, a force will just cause it to move. So what that means is when we pull on this structure at E with this 300-pound load, that all of that 300-pound load is going to be reacted to at point D. So we'll have a 300-pound reaction going back into the wall at point D that puts the structural member in tension. All right, so he also tells us that 150 pounds is applied 2 feet to the left of the cut, or 2 feet to the left of D, which is where we cut, and we cut at 4 feet. So we're actually cutting 2 feet beyond that 150-pound shearing load. Now the thing to notice about this 150 pounds, it creates a tau in the amount of VQ over IT at both points A and B on the cut section. However, it also is going to create a bending moment, isn't it? So we have 150 pounds applied 2 feet to the left of the cut. So on that cut, we're going to have a bending moment, which is going to increase or decrease, depending on where you are on the cut face, the total sigma. Because the 300 pounds will produce a P over A sigma, but the 150 pounds will produce an MC over I. And so you can see that point A is above the neutral axis, point B is below the neutral axis. So sigma at point B from a bending load is going to be positive because it's in tension, and sigma at point A is going to be negative because it's in compression. All right, so here's my solution. We go ahead and we look at, now that he cuts it, and he also likes to cut it the opposite way. I always like to cut from the left to the right. He likes to do it the opposite way. It's equally valid. But the first thing we do is we do statics, and we find out that the reaction here at point D, right here, is 120 pounds. The reaction here at point E is 30 pounds. And so when we do our free body diagram, we draw these directional ideas. He draws this one down. So once again, we have a little bit of discrepancy in terms of how we call our, it's not really how we call our sign convention. He uses the same sign convention generally, but we are drawing our V force down. Right, so there's the free body diagram operating this way, coming 6 feet over to the cut face. All right, and we calculate our reactive load V, we calculate our reactive load P, and we calculate our moment. He always indicates that it's clockwise, 180 foot-pounds. This S, it bothers me as well. It really shouldn't be here, but that's neither here nor there. If you notice, he defines a positive moment as being clockwise, right? So that's the idea that he has right here. So the moment that he's actually drawn here is counterclockwise. This is clockwise, so it's negative. But when he does that, he comes up with a positive moment, meaning that it's clockwise. All right. Now, continuing with that idea, we can find our sigma at point B, and we can find our sigma at point A. Now, I had said that B was going to be in tension, and A is going to be in compression, but now I can see that that is the opposite because this is actually a downward acting force. So B is in tension, B is in compression, pardon me, A is in tension because this is bending downward, isn't it? It's bending in a negative or smiley, frowny face configuration. All right, so we get a value, MC over I, for our sigma at B, and we get a sigma at P over A. Now you're also going to have all right, this is kind of strange. Hang on just a second. All right. He sort of got a little bit of a mix-up on, or not a mix-up, but a confusing point on his symbols. We're taking a look at point A. So this is not really the sigma at point B, as I think would be indicated from the drawing. What this is the normal stress due to bending at point A. So coming back here, we're talking about this point A. All right? And so if we take a look at that, this is our P over A load, which is just from the axial load, and there's no torsion, so VQ over IT is the entire tau. So, but we have these two values to add together for sigma total, and one of them is in compression, one of them is in tension. So basically what we find is that sigma total is in compression, which we might call negative. Now, tau total is just this. But the thing that bothers me is this is at point A. So what I'm pointing out to you is he uses this tau of B a little bit loosely. But basically what he does then is, this is a technique called a stress block, which we will be using for parts of our solution, where you label just a little cube of the material. And what that means is, if you go up here at point A, you're just going backward into the structure just a little tiny bit, and you're taking out a finite element at point A, and then you're drawing what's happening to it in terms of stress. Not in terms of load, but in terms of stress. So what he's saying is at point A is in compression by 31.85 psi, and it has a shearing stress of 2.1 psi. Now the one thing that I also want you to recognize is sigma is an axial phenomena, happens on a single axis. So you'll notice that 31.85 psi is counteracted by an arrow, by just takes two arrows. In other words, pushing this together prevents it from moving. However, with tau, what you'll see is there are actually 4 arrows. There's one set of clockwise arrows on the top and the bottom, and one set of counterclockwise arrows on the two faces. That's because if we just had this and this, it would spin in a clockwise manner. If we just had this and this, it would spin in a counterclockwise manner. So it actually takes 2 moments, or one clockwise and one counterclockwise moment, in order to keep that from spinning. Now let's look at the cut face here. We understand the sigma being negative or in compression, but let's look at the cut face. The V force, or the tau force created by V, is going down. So I'm going to go back to the original diagram, and you can see that that's the way that he had drawn it at that point. All right? So that's the origin of the sign. You think about the cut face as being the very edge of this item, and then the rest of it goes back into the beam just a tiny little bit. And you'll notice that here the cut face is on the left, and here the cut face is also on the left. Now if I'd cut it the opposite way, I could put my cut face over here, and I would see that it was up instead of down, which just makes sense because it's not really going anywhere. It's just a reaction, and it depends. One lamina on one side or the other, the direction changes because it is actually overall equal to 0. It's because it's not moving. All right, so then we do the same thing here at B. And we have a B is in tension. We have both we have a P over A force here at B, and we have an MC over I force, and they're both in tension. But now look what happens at tau is VQ over IT. We know from our previous discussion with this formula that Q is the first moment away from the neutral axis. So let's go back to our drawing. And what you see is that point B is at the very bottom. So there's no shearing stress at point B, is there? Because Q is equal to 0. VQ over IT, if Q is equal to 0, then that entire expression is equal to 0. So the stress block at B, we just have the two sigmas added to each other. So in other words, the magnitudes add. Here at A, they subtract from each other, but here at B, they both add. And so B is in tension only, and there is no shearing stress at point B. All right, so this gets us through the idea of using a stress block for analysis and the idea of a combined loading scenario. I'm going to give you a couple of homework problems in the back. By the time we finish this section, we will have completed all of the homework from this handout, and there are a total of, I think, 11 problems. Yes, 12 problems, and some of them kind of reuse the data. But if you look at problems 6.1 and 6.2, these are very similar to the types of problems that we just did in this example. And so what I would like you to do for homework tonight are problems 16.1 and 16.2. Then when we come back on Monday, we'll talk a little bit more about torsion and how that adds to the tau value. So we'll do a couple of more problems. And then beginning on Wednesday, we're going to start with stress blocks and use a technique called Moore's circle to do the stress analysis. So for tonight, let me come over here to the document cam. For tonight, 12-2, do problems 16-1 and 16-2. And on Monday we'll talk about torsion, and Wednesday we'll begin talking about Moore's circle. All right, thank you, ladies and gentlemen. Have a wonderful weekend, and we'll see you Monday.